This is chapter 14, the assess section, starting at page 207 and working forward. Probably take about 2 or 3 videos. I'll try and keep it down to 2. This is question 4 and it's rated between grade C and grade B. So here are similar triangles. In other words, this 3 relates to that 3.3 by a certain enlargement, a certain scale factor. That 3 relates to this question mark here. The height of 2.4 relates to the mystery height there, and the base of 3.96 relates to the base there, because these triangles are in fact similar. Now find the ratio of the corresponding sides in the form of 1 to n. Okay, so it's working blue. So that one to that one, we now have 3 to 3.3. In order to give it in the form of 1 to n, divide each side by 3, and that will give us 1 to 1.1. Is that alright? Too many ones there. Anyway, that's that. And the same with each side, really. The ratio of the sides, I can only directly relate the 3 to the 3.3. I presume this is an isosceles triangle, in which case that will be 3.3 as well. But we'll just leave that alone. Then it says find the missing length. So okay then. So that's part A. Now part B, find the missing lengths. Well, I know the enlargement is going to be multiplied by 1.1. So I'm going to go from 2.4 to this mystery height multiplied by 1.1, and let's put the answer just there on this side here. I won't show all the steps. So I'm saying 2.4 multiplied by 1.1, that will give us a height of 2.64. Working backwards with this one, in order to scale this back down to the original base, I just wanted to divide by 1.1. So I'm saying 3.96 divided by 1.1, and that's giving me exactly 3.6 as a base. Let's put that in red. So let's do answers in red then, shall we? So 3.6, and well, if I've got a 3 there, this must be 3.3 as well, for the simple reason that it corresponds to this 3, and that 3.3 being friends, then this 3 must relate to this side, and so straight away that's 3.3. No calculation required. Essentially I'm taking 3 multiplying by 1.1 to get 3.3. Right, so I found all the missing lengths, I believe. Yes. Find the area of each of the triangles. Okay, so that's been done. Back to blue. Okay, area. So this little one here, half times base times the height. We'll just get one answer for that one quickly. So 0.5 times 3.6 times 2.4, and we've got ourselves 4.32 centimetre squares. Now this side, half times base 3.96, multiply the height of 2.64, and that's going to give us 0.5 times 3.96 times 2.64, and that gives us 5.2272 centimetre squares. And it says find the area of each triangle. Okay, so that's been done. Give what is the ratio of the areas in the form of 1 to n. Now give it to 2dp. In other words, it's not going to be very pretty. So part D, ratio. Well, let's go 4.32 to 5.2272. To make the left hand side 1, you just divide by 4.32, and therefore to keep the ratio trimmed down by the same proportion, also divide by 4.32. That gives us 1. Just work out this little bit here. Divide by 4.32, and that gives us 1.21. So that's my ratio to 2 decimal places. I didn't need to round off anything. That's just how it worked out. And there's your grade B then. Now, over the page, I'm looking at my textbook here. This is me working on question 6, I believe. No, it's not. It's question 5. Okay, question 5 it is. It says draw a pair of axes. Well, I've done all that. -10 to 6, etc. in both directions. Plot these coordinates, and I've done that, and that's triangle A. I've done that to save time. Now draw the image of triangle A after an enlargement of a scale factor of 1/4 with centre 4, 2. So I've plotted the point centre 4, 2, and that's the centre of enlargement, as you know. Let me just relabel it. let's just draw back the rays using this facility. Let's go for red. That's that. That's that. And that's that. Now if I've got it absolutely perfectly, I should be able to do enlargement of a quarter coming from that centre of enlargement there. Essentially, we had a ruler, I can measure the distance from each vertex to the centre, or from the centre to each vertex, and divide that by 4 and replot the coordinates. Now if you know me at all, I tend to do it by calculation purposes. Now let's do this easy one here. From here to here, if I just count squares, 2, 4, 6, 8, 1, 2, 3, 4. If I quarter 8 across, I'm going to be only 2, aren't I? So 2 away, and let's take a look there. 1 down. Right, so that is that. Okay, so 2 across and 1 up is a quarter of 1, 2, 3, 4, 5, 6, 7, 8. Yep, quarter of 8, and it's a quarter of 4 up. So instead of going 8 across 4 up, I've gone 2 across 1 up, and therefore that automatically shrinks it down to a quarter. It's still called enlargement, don't forget that. Now, without any further ado, I can now use my construction lines to take this equivalent vertical drop from there to there, and do the same from here to here. So I'll also do that in blue, and we'll work with that facility here. So it's not perfectly accurate, but this is what I'm doing. I'm using my construction lines, and look, I know this goes to the left from this point to that point, so I'm going to take this to the left there and just drop it onto that construction line, then just join the ends. Now it'll be far more accurate on pen and paper, obviously, working in class and graph paper and what have you, but essentially what I've done is to reduce this down to a quarter of the size, scale factor 1/4. This is triangle B. I'll put it there. It'll make too much mess if I put it there. And that's the image. So that's the image, and that's the original object, which has been enlarged by a scale factor of 1/4. Alright, so that's how it looks. It says what the coordinates of the vertices of B. Well, let's try and do this one, shall we? Well, this one's going to be 2, 1. So let's just try and list them. It's not very clear at all. Let's list them to the side. So 2, 1 will be that one. 2 minus 1 will be that one. And that's going to be 1, 1 right there. Okay. Again, these can be proven mathematically where they are located in relation to this enlargement scale factor of 1/4. It can be done mathematically, but I can see that for the relatively accurate on-screen diagram, I can read it off my diagram anyway. And that's question 5 done up to grade B. There's also a question 6 grade A. I'm not going to do that. I've done so many in the previous videos, so I'm going to stop there. Now, question 7, I believe, yes, it's definitely grade A, says that the area of a trapezium is 12 centimetres squared. Clearly it's an area because the unit is squared. It is enlarged by a scale factor for length of 4. Now listen, scale factor for length. In other words, a linear ratio. So let's write that down. The linear ratio of enlargement is 1 to 4. Okay? Now what is the area of the enlarged, the bigger trapezium? Well, the baby one's only 12. We don't multiply the small area by 4 because this is just the ratio for the linear lengths, the sides of the trapezia. The corresponding sides, if you will be in the ratio of 1 to 4. So for example, a little baby trapezium like that may have a length here of 2, and big giant trapezium over here will have a length of 4 times that, which will be 8, for example. And this will be in centimetres, okay? So that is not what we're doing. We're playing with areas, and you may recall that the area ratio is going to be the linear ratio squared. So it's 1 squared compared to 4 squared. In other words, 1 to 16. So the area is in fact 16 times as big as the original, not just 4 times. So therefore we can take our 12 centimetres squared, excuse me, that's the baby one that corresponds to the 1, and multiply that by 16. We're going to get a nice big answer, aren't we? So 12 16ths. Boom, 192 centimetres squares of area. Alright, Lovely, lovely question. I think I'll do one more and then just pause the video for a separate go. Right, here we go. This is the first AQA question on page 108, and it's question 1. It's straightforward, I'll do it anyway. It says, in the diagram, shape B is enlarged, is the enlargement of shaded shape A. So B is the enlargement of A. It's obviously shrunk down a little bit, but it's an enlargement, okay, don't forget that. Write down the coordinates of the centre of enlargement. Okay, so let's just draw some lines from one corresponding point to the other. Alright, so I think that's that one. No, I think that one joins to that one. And it looks like I'm getting a centre of minus 1, 0. Let's try another one. Join this one to this one and see if that also works. Yes, it does. Okay, I'm pretty convinced. So the centre of enlargement is minus 1, 0, and I'm going to write that down. So minus 1, 0 is our centre of enlargement. Write down the scale factor of the enlargement. Now let's read it very carefully. B is the enlargement of A. So I've gone from big to little. Now look at it very carefully. My base is 1, 2, 3, 4. My transformed base is only 2 units across. Therefore I've shrunk down to half the size. So there's a half in the answer somewhere. But look, it's flipped back on itself and gone through the centre of enlargement right there. And because it's passed through the centre of enlargement and we construct the shape on the other side of the centre of enlargement, it's become a negative scale factor. So not only is it half the original size in terms of the linear lengths, it's also a negative scale factor of minus 1/2. Okay, check again. The original is 4 units tall, the small one is 2 units tall, that's a half. The original is 2 units across the top there, the small one is just 1 unit, that's half. Alright, so that's negative half. That's that one. I think I'll pause there and save the remaining 2 AQA questions for a second video, and then that'll be it for this chapter.